day for me because we have been exchanging and communicating with Aaron the last 3-4 years over the internet virtually, and finally we have managed to bring him here and meet in person. So thank you all for joining us. I'm going to say a few words about him. Aaron Specher is an associate professor at the Technion Israel Institute of Technology at the Faculty of Architecture and Town Planning. He leads the Material Topology Research Laboratory and the Center for Advanced Manufacturing at the National Building Research Institute, and is co-founder and partner of the award-winning practice Open Source Architecture, a collaborative research group that works in the fields of design, architecture, engineering, and media research. Before his affiliation with Technion, he was at the McGill University, and before that he taught at Syracuse University. While at McGill, he was awarded a series of research grants, including the prestigious Canada Foundation for Innovation Research Grant and 2 Social Sciences and Humanities Research Council grants. His research focuses mostly on synergies between information technologies, computation, and digital fabrication, examining the way in which technology can inform and can help us generate innovative approaches to design. Aaron has lectured in many institutions, including the MIT, the Harvard, the Rhode Island School of Architecture, or RISD, and Rice University. And today he will be talking to us about the potentialities of architecture, and we are all very curious to hear what this means. So Aaron, the floor is yours.
Thank you. Thank you so much, Georgios. It's a pleasure to be here. I first, of course, would like to thank the Cyprus Institute for your kind invitation, and Professor Georgios Artopoulos. And as you mentioned, Giorgio, for me, it's also meaningful and important to be here after all those years of working together, also with Salvatore, and to be finally with you after hard work on the ECCI initiative that was such a successful operation, I believe. And for me, coming from Israel, it was even more meaningful, as I shared with you, with the fact that I could be suddenly in relations with so many colleagues from the region, colleagues with whom, for multiple reasons, we are not always in communication, but then we came to realize that the environment is this sort of common topic that we have to share and that we have to discuss, no matter what are the borders, being cultural, social, or political. So for me, it is really a pleasure to be with you and to share with you today a few thoughts about the state of architecture, in my opinion, in the age of what we call commonly the Anthropocene. I feel especially honored because some of the things that you will see today you don't know that, Georgios, but some of those things actually stems from the discussions that we had in the past few years. And that shows how influential can be a discussion with colleagues and with friends in academia. So I'm actually delighted to pursue this discussion today with you across those projects. And I have prepared for that, I have selected specific projects that we are developing in our laboratory at the Technion Institute of Technology. And specifically, I will concentrate on those projects because I think that, whenever you give a lecture in a different academic institution, it is always interesting to actually share what's happening in other institutions, and I hope this will help us to pursue our discussion for many more years. So I will start with this, a few pictures from our laboratory at the Technion, and a few thoughts about information technologies. I believe that information technologies have transformed the way we perceive our human environment, and prior to the last 20 years, I think that information technologies were considered outside of the architectural discipline, and architects who experimented with digital processes were seen as transgressing their disciplinary boundary. Pioneers such as Yona Friedman and Nicholas Negroponte carried architectural knowledge into the realm of digital technologies to experiment and generate new knowledge from operating in an alternative context that offered new possibilities. These first moments of what we commonly call today digital architecture are of a high interest at our lab. The work of architect Yael Engelhardt, one of our recent graduates, exemplifies this condition. Yael worked together with the famous French-Hungarian architect Yona Friedman in 2018 until he passed away. And she worked with him to reenact a software that Yona Friedman designed with the Architecture Machine Group at MIT in the 1970s. This software was called Yona, Your Own Native Architecture, and is actually what I would consider to be the ancestor of what we call today parametric software. Another example of such an interest to bridge architectural theory and practice is this ongoing research by graduate researcher Tamar Levinger at our lab. Here, Tamar investigates a series of exhibitions that took place in the first days of the digital era. The objective is to map and analyze the multiple discourses that appeared in the emerging field of digital culture then. Observing these experimental years of digital architecture contributes to the understanding of the profound impact of technology on the way architectural objects are conceived, iterated, simulated, analyzed, and produced today. So, in a recent book entitled Instabilities and Potentialities, we actually identified together with my partners 3 main shifts in the way we approach architecture in the age of computation. And here are, I would say, the 3 things that I would like to discuss with you across the projects today. The first, it's a movement from an abstracted mode of codification to the formation of its image. And what I mean by this is that prior to the use of computers in architecture, we were actually conceiving forms and objects from preconceived ideas that we had. We had a certain idealistic idea about the architectural object. The computer gave us the possibility to actually program those forms. In other words, instead of drawing an object and being within the visual realm, today with computers we are actually codifying first, we're programming the machine, so we're working within the non-image realm, and then we're looking on the computer, on the screen, to see how the image is coming up, how the object is emerging. So I think that that's a major shift in the history of architecture. A second one is the idea of, or that movement from formal to statistical architecture. In other words, that movement from conceiving the architectural object as being idealistic to the idea that an architectural object could have multiple solutions thanks to the power of computation. And the third element, the third shift in architecture, I think that is absolutely crucial, is actually this idea of the convergence of knowledge. That is an opportunity to bridge historical and design practices, scientific and haptic modes of design thinking, and above all, local and global cultures in manufacturing. So I propose to discuss a series of projects now and research that are ongoing or recently completed at our lab, MTRL, and each of these projects reflect a particular relation to architectural practices and methods that contributes to what we commonly call cultural sustainability. The following projects reveal the potential of addressing the notion of cultural sustainability in architecture. Just to remind you, in a recent report from UNESCO, cultural sustainability referred to maintaining cultural beliefs, cultural practices, heritage conservation, culture as its own entity, and the question of whether or not any given cultures will exist in the future. This is a definition that comes out from the UNESCO website. From cultural heritage to cultural and creative industries, this report from UNESCO refers to culture as both an enabler and a driver of the economic, social, and environmental dimensions of sustainable development. So if we talk about sustainability today, while we commonly talk about environmental sustainability, we should also think about cultural sustainability and the way local cultures and communities are also part of that equation. So I will start with the first project by Dr. Tom Shaquet, who recently completed his doctoral thesis entitled Technical Uncertainty toward a sensible architectural tool. Tom Chacquet's work considers the potential of reenacting ancient modes of architectural manufacturing in the age of automation. His work addresses the need to communicate sensibility to the robotic tool while shaping the object. So here is the story. It starts here in Jerusalem, a city whose facades are covered with Jerusalem stones. Here you see the Grabelski family that runs the last factory that is capable of stone cutting and dressing in the region. The disappearance of this industrial field in the region results from its competition with alternative industries such as ceramics and synthetic materials, but also a lack of skilled manpower and a loss of historical knowledge as reported by Tom Chacquet. Our Middle East region has a long history of using stone as a central architectural element. Conrad Schick, an architect and archaeologist who worked in Jerusalem toward the end of the 19th century, described in detail the features of the chisel marks on the stone walls of the Zetekia cave, one of the most ancient quarries located in Jerusalem Old City. Tawfiq Kanan, a Palestinian doctor from Jerusalem and the director of the Hansen Hospital in Jerusalem, described the local construction methods with special emphasis on the different types of stone and the cutting tools that were then used. This legacy is still present today in the Jerusalem Master Plan, in which it is stated that the outer walls and pillars of houses, I quote, will be covered with natural, finely dressed stones. This is the reason why the entire city of Jerusalem until today is covered with stones. Even the Standard Institution of Israel references traditional stone dressing method and provides a detailed account to the different patterns of stone finishing. As Tom Chacquet reports, in a recent visit to the Grabelski factory, there were signs that in the last decades, the stone industry had undergone a transformation from manual labor to the automation of production processes. Nevertheless, if one looks closely at the end of each stone process, as you can see here, there appears to be still a demand for skilled stone craftsmen to carry out complex custom tasks. In other words, machines are being used, but machines are not capable until today to really do the stone cutting and the dressing as needed. So considering the need to address the parameter of uncertainty in the craftsman's gesture and the unpredictability regarding the process material, Tom Chacquet proposes a human-to-robot craft method that translates the craftsman's tacit knowledge, that is a set of skills and abilities, individual gain by experience, and often difficult to communicate verbally. So the whole idea is how to communicate this tacit knowledge from the craftsman to a machine. Tom Chacquet proposes to envision a practice in which a robotic arm is taught to react to specific material scenarios, similar to the way craftsmen would. In his own words, this research extends existing knowledge in digital manufacturing based on the notions of technical indeterminacies and sensibility. So for each case study that he did, the research employed a research by design method in which he first considers the action that is expressed with a tool or a method, produce specific objects, and then examine them as a valid research outcome. And therefore, an alternative to the typical top-down approach emerges, an alternative that addresses the complexity of robotic fabrication with a bottom-up approach that arises as a result of specific material conditions by relying on accumulated human data and autonomous processing abilities of local sensors. So let's just see a few examples, a few experiments that he did, and that brought him to actually develop a whole technology that is today patented. In this first experiment, a brush tool equipped a robotic arm, and it's also mounted with pressure sensors, so that he could actually start experimenting with robot adapter, the idea of a flat brush that would be moved by the robot, and an open source load sensors. And so what you see here on that screen is a custom developed real-time communication protocol that mediates between the sensor and the robot. While the robot is the moving platform, the sensor on the brush is situated on the tip of the brush and is capable of conveying the sensation back to the robot as to the pressure that is happening on the paper. In a second experiment, aside from touch sensing, Tom explored the use of machine vision to produce real-time robot toolpath. Here we see Tom's collaborator, Uri Dubin, a neuroscientist, who controls the robot using hand gesture. In a third experiment, Tom employed object detection method to produce real-time robot toolpath. While this is a complex task for the robotic arm, it is actually easy for a human to do it, and yet it is actually very complex to program. Here is actually now a fourth experiment that you see that has to do with sand that is scattered on the table, and the robot is instructed to form it into a pile. The iterative process begins by analyzing the dispersed and geometry and producing an ad hoc motion plan, brushing toward a target location. For every brushing cycle, the plan relies on generating a vector field which is dispersed evenly across the sand geometry. Following each cycle, the robot allows the camera to survey the outcome and produce an updated image. The robot repeats the process until the desired result is achieved. Here, 5 stones are placed on the table, and the robot is instructed to arrange them in a circle. For each stone, a vector is generated from its current location to its target location on the desired circle. This approach includes identifying and tracking each discrete element. These experiments provided a basis for developing the method and appropriate setup for the core experiments of the research. It mediates between the deterministic nature of the software and the sensible dimension of the fabrication tool. For that purpose, Tom Shaquet developed Reflex, that is a grasshopper application capable of craft-oriented robotic fabrication by employing 3 primary capacities: image processing and object detection, as you've seen, computer vision and 3D reconstruction, real-time robot control, and predefined fabrication modules. On the Rhino Grasshopper side, Reflex provides an agile framework for craft-oriented fabrication. It is organized around several capabilities responding to the challenges arising from uncertain material behavior. Here, for instance, you can see an integration of deep learning capacities into Reflex that enables image classification for material analysis. And I can already see a lot of application, in preservation, in archaeology, and in the way I know here in the Institute, you are, tracking down historical material. So Reflex computer vision module can also be performed for failure detection during fabrication, for instance, like here, on the Western Wall in Old Jerusalem, where we can actually track the multiple, I would say, discrepancies that you would see, on the surface. So back in the Grabelsi factory, a stone carver is removing the sharp edges of a custom-ordered stone. His capacity lies in the sensibility he applies using carving tools, which allows him to respond differently to the unpredictability presented by each stone. So addressing this condition, Tom offered a unique research method for performing adaptive robotic carving. 3 main stages: human-robot craft, robotic tools development, and then experimentation and validation. That first stage employs motion capture techniques to record and analyze the gesture of craftsmen at work. The chisel is mounted with an adapter consisting of 5 markers. Each marker receives a unique ID and is used to construct the adapter in 3D and derive the chisel's position and orientation in space throughout the carving session. The documentation phase provides an initial database for analyzing the 3 carving techniques. Following each session, the trajectories were reconstructed and exported as 2-dimensional arrays in an Excel format and visualized using Python. Lastly, Tom developed a computer vision application allowing to detect the total amount of material removed from the stone surface for each chisel stroke. And an end effector was then included in this research, a pneumatic hammer that connects to a variety of chisel. I'm not sure if we will be able to, here we go. And this end effector of the robot is capable of replacing the traditional manual hammer, a linear axis that brings the chisel back after each blow and replaces the second hand of the craftsman. So the robotic setup for the stone carving experiment consists of a large industrial robotic arm that is installed on a linear rail at our lab. The toolkit consists of a custom-designed multi-chisel carving and effector. Tom Shaquette's PhD research on technical uncertainty explored the potential of craft-oriented robotic fabrication in the face of a decline in manual craftsmanship in architecture. Despite the growing availability of digital tools, these tools are still limited in terms of their capacity to perform custom, high-skill tasks. This limitation stems from the challenges presented by unstructured environments, material uncertainty, and the physical distance between the designer and the manufactured object. So his research and subsequent patents extends existing knowledge on digital manufacturing, proposing to integrate sensory data and manual capabilities into architectural production using industrial robots as a platform. Project number 2. Territorial-based robotic fabrication. In her recent completed research, doctoral research, Dr. Karen Libar-Sinai from our lab engaged with the notion of technological sensibility and robotic fabrication at the very large scale this time. That is, the territorial scale. Her thesis first addressed the notion of informing grounds, that is, the capacity to shape grounds to a desired form or performance. Beyond its performative aspects, Karen Libar-Sinai's work questions the notion of cultural landscape, or in other words, the significance of the human action on marking and shaping its environment. And so I would like just to share with you that image, the rest or the traces of a Nabatean city in the south of Israel in the Negev desert. And in the words of Karen Libar-Sinai, we must be humble about our future and our efforts, because this is an excavated structure from which we can actually learn, from which we can actually emulate a new technique or a new knowledge, advance that knowledge, and not just simply reproduce it. And this is what Karen Lee has been doing across multiple courses that she's been teaching at the Technion Institute of Technology. And you see here her students with her visiting some sites in the Mitzpe Ramon crater in the middle of the Negev desert, and the way they've been actually looking into locally found material, how to stabilize those materials and use them in multiple digital fabrication processes. In her research, she used an MTRL setup for informing grounds that is based on the notion of bridging scales, or in other words, the possibility of simulating ground formation at a laboratory scale while envisioning its capability in terms of a territorial scale. These scaled experiments offered the possibility to test the relationship between the robotic motion, the tool, and the material at hand. In her work, Karen Libar-Sinai tested 3 kinds of toolpath motion and their respective topographical effects. What we see here are tests on a linear motion. Linear motion is a robotic action of flattening and creating divisions between different areas. This motion was most effectively performed using a simple wide edge end effector. A third forming pattern tested was curvilinear motion. In fact, in the previous one, there are actually 2 patterns, one that is actually using a sharp edge end effector, another one with a round end effector. And so there was a third forming pattern that she tested with of curvilinear motion, in this case a robotic motion that aimed to form subtle undulations by employing a continuous sinusoidal toolpath. To support this process, Karen Lee developed an iterative fabrication protocol for informing grounds. In testing the three motions, linear, pressing, and curvilinear, Karen Lee Barsinai concludes with three things. One, subtle changes in the toolpath edge produce distinctly different effects. Two, intricate effects can be attained by simple tools. And three, limiting the tool shape to a single point or edge allows a higher degree of control in the sand forming process. And finally, so there is a fourth point, calibrating additional parameters such as the robot speed and its tool center point can enhance the toolpath effect on the results. Karen Lee Barsinai's approach to material landscape envisions the capability for reconstituting geomaterials that is defined as modulating locally found matter into construction material using robotic tools and additive manufacturing. In her work, she looked into a Negev desert site and conducted mineral profiling for geomaterials drawn from it, including a mechanical and chemical analysis with the long-term goal of developing a recipe for a cementitious material using locally sourced aggregates. So she started to test all this at a small scales using 3D printing techniques where an extruder was filled with mixtures of side sand and various binders. These strategies served as a basis for exploring procedural robotic fabrication, a robotic process which starts with earthworks and robotic ground forming through 3D printing of the elements on site, and finally with the assembly to a structure on the formed ground. In this context, she tested methods for constructing parts produced by additive manufacturing using a technique that she calls discrete additive, meaning 3D printing the different elements as independent elements that can actually interlock into a structure. The architectural system featured an open roof structure composed of 3 layers of stackable hollow elements. All what you see here are actually works that she's been developing in her own class with her students. It is here proposed, according to Karen Lee Barsinai, a new method for additive manufacturing that is combining the conventional method of continuous additive manufacturing with modular additive components that can be actually brought on site and that can be repositioned by a robotic tool in order to create and build the structure. And so this is actually a strategy that is based on repositioning the robotic tool on the site to produce this continuous segment. And these continuous segments are then overlaid with discrete elements in various forms, as you can see in this catalog, for instance. Beyond the contribution of a fabrication protocol, Karen Lee Barsinai's thesis develops a comprehensive qualitative and comparative analysis between methods of on-site additive manufacturing. It expands terminology regarding in situ robotic fabrication and on-site 3D printing and highlights the benefits of combining various methods of expanding scale and feasibility, especially for low-income context. 3. Computational extrusion for earth construction by Ofer Asaf. What you will see now is actually in the continuity of what Karen Lee Barsinai has been proposing in her thesis. Ofer Asaf is currently investigating some of the agricultural sites that you can find in the desert of the Negev, and he's looking into ancient communities and the way they were harvesting the desert. As I was sharing yesterday night, the Roman historian Flavius Josephus is describing the Negev desert in the south of Israel as a land of wineries and flowers. In other words, in ancient communities, mainly in the Nabatean period, they knew how to harvest rainwater. They knew how to use that ground in order to produce an agriculture. We have lost that knowledge, and here at our lab, we are trying to reenact it in multiple ways. I'm showing you this picture at Wadi Zedan, to share with you what's happening with olive trees in this region. And I would like just to bring your attention to what's happening in the back of that tree, where you can see a little wall of stone that is a remain of a Nabatean wall that surrounded that, that location. In other words, the Nabateans were were producing microclimates by building little walls around certain areas in order to harvest and create their own agriculture, in this case, to grow trees. This is what Ofer Asaf is doing in his current PhD at our lab. He's addressing first, his research is actually in is covering two aspects. First, how to use locally found materials in manufacturing processes. And in the second part of his PhD, it is about applying that to that ecology, or that new ecology that he sees for the Negev deserts. Ofer Asaf addresses automated fabrication processes by investigating the fundamental relation between design method, tooling, and material. Referencing the work of Karen Libar Sinai, Ofer first analyzes and reduces locally found aggregates to reach a particle size that would be optimized for additive manufacturing. Using an iterative method of testing, the soil-based material that you see here is combined with 100% environmental materials, including fibers, in order to reach a structural and mechanical property capable of sustaining its own weight. There are no chemicals whatsoever within what you see here on the screen. It's all made out of soil, water, and fibers. Ofer Asaf's approach to what he calls computing materiality provides the scientific context to define the multiple material aspects that must be taken into consideration for additive manufacturing optimization. Using this system, Ofer produces iterative experiments to optimize the material composite for 3D printing of soil-based structures. These iterative experiments provide fundamental data regarding the material behavior in additive manufacturing processes. What you see here on the wall are a series of experiments and objects that he's actually producing, where he's actually looking about how to create that synergy between the material definition, the tool that is extruding the material and 3D printing with, and then the object itself and the way that object is behaving structurally, mechanically, and in its environment. Ofer research stands at the crossing of quantitative and qualitative assessments of material performances. His research methodology provides the conditions to both consider the visual and physical behavior of distributed soil-based material and their rheological properties that are key to any additive manufacturing processes. The control of additive manufacturing parameters such as the distribution velocity, the material elasticity, and its curing generates formal effects that may influence the formal manifestation, as you can see here on the screen. The speed of the robot, the speed and the rheological properties of the material itself as it is being extruded is actually creating those different effects that you see here. The work of Ofer Asaf provides a scientific approach to the fundamental relation between tooling, material, and design in the formation of the object. Such an assessment is complex as it requires taking into consideration many parameters that are internal to the material composite mixture, the type and design of the manufacturing tool, the method of material deposition, and the design definition of the object. Ofer is currently optimizing this relation between design, tool, and material with the objective of producing in the coming year a full-scale architectural element that will dramatically leverage the environmental impact of architectural construction in our region. More so, his current work stands among the few research that are today scientifically probing. He's publishing all that. It's all open, to the difference of many companies today that are actually developing those technologies privately, and therefore we have very little data as to how they're getting to their results. In our case, since we are academics, we're about to share all that. Ofer Asaf, together with the MTRL team, here with research assistant Ronnie Hillel, currently apply this fundamental knowledge to ongoing projects with partners from the Faculty of Civil Engineering at the Technion, Professor Arnon Bentour, a world expert in cement materials, and Oded Amir, one of the top scientists in the field of topology optimization. Here's some of our recent experiments on high-performance concrete mixture that we investigate in partnership with the Israel Ministry of Construction. Our composite mixture and additive manufacturing method targets a reduction by 50% of construction material compared to conventional method of concrete casting. So I can announce to you that we know how to make it 50% cheaper, or at least, you know, we would be able to construct with 50% less material with this kind of technology. So now I would like to show you one of the very first projects that launched our lab about 5 years ago. This is a project by graduate researcher Ryan Purati. I like to say that together with Tom, Karen Lee, Ofer, Ryan has been definitely key to the building of our lab. As you just seen just before, concrete is in fact the primary construction material in our Middle Eastern region. Our landscape is rich in minerals and aggregates such that cement material are predominant in the construction field in Israel. So if you ask me, as an Israeli architect, researcher, to build in wood, I have no knowledge of wood because we don't have wood in our region. But if you want to build with stone and aggregates and sand, I'd be happy to help. The following research by graduate researcher Ryan Purati not only innovate in the field of concrete manufacturing, but foremost mark a paradigm shift for this industry. Just to show you a little bit of the context, this is Tel Aviv. Tel Aviv is marked by the 1960s, what we call Israeli brutalism. So lots of very brute concrete buildings in the city of Tel Aviv, as well as Beersheba and in most of the country. This is, by the way, what you've seen was actually the 1972 Museum of Art in Tel Aviv, and this is actually the last extension by Preston Scott Cohen that is also using concrete, but in very different ways. And you see here a panelization of concrete slabs that is actually forming his architecture. In the following research, Ryan Purati envisions manufacturing very lightweight concrete architectural scale components using a method of rotational casting that conventionally belongs to the plastic industry. Ryan Purati's stunning research holds multiple US patents today. And I'm saying this because what is stunning is that this is actually a prototype that Ryan Purati did of his research as he was completing his first degree in architecture. Already then, he was thinking about a patent. The machine that you see here allowed him to manually produce his first proof of concept. The principle is to place a mold at the center of this machine, in between those two frames, and the mold is actually filled in with the material mixture. The material inside the mold is then distributed in all directions thanks to the centrifugal force generated by the rotation of the two frames. Here is actually one of the first complex shape modules that he produced using that method of rotational casting. The element that you see here, just for you to understand, because it's on the screen only, is about 1 meter dimension. It's a beautiful architectural object. Okay, it's at the scale of an architecture. And the thickness of that object that is made in concrete is 2 to 5 millimeters. So it is hollow. And the idea is how can we actually reduce dramatically the use of concrete as we are building architectural elements using this technique. This object is actually incredibly strong and is only 2 to 5 millimeters thickness of concrete. Subsequent experiments investigated the potential of including different types of fibers and textiles within the mold in order to reach high-performant mechanical properties. You see here a whole range, and we have many in the lab, many experiments that he did, trying to actually refine the concrete mixture in relation to those to the use of those fibers. Ryan Purati's research on architectural scale rotational casting addresses the required synergy between material definition, tooling, and design method. What you see here is the typical robotic setup that includes a zone for cement material preparation, a unique rotational casting robotic cell that we designed, and that provides us with all necessary controls on the manufacturing process, and a zone for collecting the end product for validation. The architectural scale rotational casting method includes the use of molds that are designed for multiple use. In this short video, you can see the multiple operations for producing these lightweight concrete elements. We are using a customized concrete mixture that is actually a concrete with a very high degree of phosphate in it for very, very quick drying. And that follows a very fast curing process such that during the rotation, that concrete is actually drying up very quickly within the mold. And we can therefore produce an element in the lapse of a few minutes. So you see here on this video the preparation of the mixture. We are producing that at the National Institute for Building Research. Our lab belongs to it. That is actually a research entity that belongs to the Ministry of Construction, and that actually stands, it's located right next to our lab at the Technion. You see here all the technicians with Ryan in white who are actually quantifying the use of the concrete and the mixtures. You see here the mixture within the mold. And here you can see that double-framed rotation. And while it is actually distributing or distributed in all directions, within a few minutes that concrete is actually drying up and is creating those hollow elements that are just a few millimeters thick. So you can imagine, that's actually what we are doing now. We are actually comparing as a benchmark the physical and mechanical strength of those bricks, let's say, in relation to a standard building block in concrete, and we have reached the conclusion that it is very close in terms of their structural and mechanical properties. So we are actually going in the right direction with this research. And you see it here. Maybe on the screen you see it a little bit, the fumes that are still coming out from the concrete as it is actually curing. Here we go. And for Ryan Purati, he's an architect, you know. The ultimate goal, of course, is to produce an architectural structure that will be made out of those customized thin-shape elements. If successful, this project will offer a method of construction that is highly environmental due to its significant reduction of material use and labor-intensive operations. Although it is made out of concrete, we can say that it is environmentally interesting to work with those kinds of techniques because the use of material is really, really minimal. So this is indeed our objective. And meanwhile, Ryan and his team continue developing high-performance concrete mixtures. You see here some of those experiments, and from left to right, you see the improvement in terms of the dispersion, the distribution of the material within the mold, just based on tweaking the mixture that is being used. Do you still want to have like one or two more projects? Yeah? Okay, because what is following is actually really interesting. And actually I left for the end what is also very much related to what Giorgio and his team are talking about these days, so we will get there. But this is actually going to be fun. In the last 20 years, there has been a growing interest in incorporating textile digital fabrication in architecture. While most research that combine textile and architecture deal with knitting, weaving, and yarn binding, only a few studies deal with a method that only our grandmother know about, that is crocheting, crochet. You know crochet? Yeah? Okay. I'm from Belgium originally. When I was a kid at school, we also had to learn to do the crochet. So crochet is actually a traditional handcraft of creating fabric out of single yarn using a hook that is capable of achieving complex 3D textiles. The following research by PhD candidate Tamar Nix at our lab is aiming to transform crocheting from handcraft to robotic fabrication, looking into its potential for architectural applications. Computational crochet depends on 3 technological levels: the mechanization of the stitch, how to make it mechanically, okay? Computation of the pattern, how to create the path, and the fabrication of a whole structure. So just for you to know, the industry of textile is today led by machines that are capable of, knitting and weaving, but those textiles are actually 2-dimensional. There is no machine in the world that are capable of crocheting. In other words, there are no machines that are capable of 3D or manufacturing 3D textile. Imagine what it would mean if we were capable of making a 3D dimensional textile that we could introduce with other materials in composite materials or in concrete and so on, and how 3-dimensional textile could actually influence the construction industry. This is precisely what Tamar is investigating. So the following research included a series of experiments to manipulate soft yarns using a robotic arm to conclude with the automatic execution of crochet stitches. The potential of this technology was demonstrated by a pavilion that you will see in a moment that is constructed of crochet textile supported by inflatable spheres. This research aims to introduce the potential of crochet as a digital manufacturing technology, opening new directions for large-scale textile constructions. The experiment concentrated on developing a novel approach for each tested craft. So we used a robotic arm, a powerful yet conventional tool analogous to the human hand in terms of movement capabilities. So the first experiment that you will see here concerns the automation of what we call a punch needle operation. The robotic arm here expresses the yarn movement. There are in fact differences in the fabric tensile level that you see here against the wooden ring. While the embroidery is handcrafted, manual manipulation can overcome such differences. In the robotic process, the code was changed for graduated heights to compensate for these tension variations that you have on the textile. In the second experiment, we look into spatial winding of soft yarn. We produced with a robot, as you can see it here, what we commonly call a pom-pom, okay, a ball of textile. This was actually a way for us to be able to actually understand the 3-dimensionality of a robotic arm as it is actually manufacturing with textile. And every time you can see here how the human hand is actually being reduced to a certain end effector that we could mount on the robotic arm. And here, finally, for this stage, we've been creating a yarn chain that is actually a significant milestone for crocheting using a robotic arm. The chain is the foundation and starting point of a crochet handcraft. This experiment involved both linear and spatial movement. Here, the robotic arm is working in space, 3-dimensionally. Not obvious, I can tell you. A designated crochet hook and effector controls the yarn movement according to the parametric toolpath. Among various positions of the hook, the short version that you see on the right appear as the most effective in terms of controlling the yarn. So you see here different variations on the robotic arm and effector, and we came to the conclusion that actually the last one was actually the most effective one. The final phase of this series of experiments looked at conducting actual crochet stitches. The most basic stitch type, that is called a single crochet stitch, was selected. Although it is the simplest stitch, it requires double insertion of the needle into an existing loop and 2 passes of yarn collection. This experiment involved a computerized model of the crochet base in managing the path accordingly. So what we did, in short, is producing manually one of those crochet textile, we 3D scan that, and we actually inform the robot about it and look into how the robot could actually reproduce it, which is what you see on the picture. And these experiments led to a first full-scale prototype a few months ago, produced within a few days. Here, the crocheting instructions were optimized using the algorithm of a team that has been developing computational crochet already for Rhino, and that team has been actually working, collaborating with us since then. It's a team that is based at the University of Pennsylvania. Inflatable spheres provided the external tension that is required in order to hold the construction stable. You see the scale that we can reach today at our lab in terms of using those textiles. Keeping the softness of the textile enables the full reuse of the material in different configuration according to specific needs. The most obvious potential of this research is the possibility to bridge traditional modes of crochet craftsmanship and the recycling of fabric for large-scale constructions. Cultural and environmental sustainability are here meeting. Okay? And so we are actually right now developing new versions of this technique for stabilizing grounds, for landscape design, for the building of temporary shelters, and so on. It's very light, it's very cheap to produce. Quickly, 2 more projects. Okay, still in shape, yeah? So this is actually a project by, I like to say, architect Anna Boym, who graduated just a couple of days ago. It's actually a project that she's planning now to move to PhD research, because after a couple of years of researching, she got so excited by the result that now she wants more of it. Okay, this it's a very different kind of project. This research suggests using machine learning techniques as a method to read the complex morphology of what we call non-planned settlements and to generate new development alternatives that preserve the traditional knowledge of local communities and also promote their cultural sustainability. Non-planned settlements, meaning neighborhoods that are actually being built by the resident without any master plan, and that, you know, we are trying to understand today, or at least to try to find a logic in the way those bottom-up approaches are being conceived. As a case study, she looked at the town of Jizr al-Zarqa that is located in the center of Israel, and Jizr al-Zarqa is a very controversial place. Historically, the town evolved in a spontaneous self-generation process, and they did that for several decades before official planning policies from the government were introduced. Now, why is this so important? What you see here is a village that has been completely planned by the resident, but the village is growing, and it's actually completely constrained. What you see is that it is constrained between a natural reserve in the north, in the south, the city of Caesarea that, you know, is marking a border, the sea that you see on the west, and then on the east, you see one of the main highways that is crossing the entire country. This village is basically stuck in between those borders. And the government, of course, not looking into the desires of the locals, have decided to create a plan. That's what you see there on the upper left part. That's the plan that the government is targeting for. And what you see on the left down image is actually the urban fabric of Jizr al-Zarqa today. So you see the difference in terms of the urban fabric between those two ideas. So the suggested method of Anna Boym is to actually use a technique and a tool that is called Pix-to-Pix, that is actually a generative adversarial network system and model that was developed by NVDA for various applications of image-to-image translation, as you can see in these examples here above, how, you know, that tool is capable of reading an image and, you know, classifying it according to a set of parameters. So in this research, Anna Boehm is using Pix2Pix as an urban design tool that is capable of learning and reproducing complex patterns that express the unique spatial qualities of the village of Jizr az-Zarqa. Above, what you see are several examples of Jizr maps with varying complexity. Each of these were tested as training data sets for the GAN model, those generative adversarial network model, in order to find the most suitable format for effective training. The purpose of the objective of the training process is to teach the model to fill the empty part of the map that you see here, based on the recognized patterns around it. In order to learn that, with each blank map, the model receives its equivalent full map. Each training dataset consists of 300 to 2,000 maps, depending on the dataset complexity, and takes several days to train. So I have a machine in the lab that is the whole day already for a couple of years, just training by learning those maps. And what you see here are actually the results of such maps. On the left is with the white square, and on the right is the result. It is what the machine is thinking that should be done after learning about all the maps and all the segments of Jizr az-Zarqa. Once the training process is complete, the model can be used on new maps to generate new urban fabric in the empty area of the map. Unlike the training process, which takes several days, the testing, in fact, takes few seconds. So the machine takes days and days to learn something, and then the result takes just a few seconds to be produced. Therefore, once the model is trained, it can be effectively used to produce multiple design alternatives, which can be further on evaluated. So just to explain that slide, on the left side, the input. On the right side, this is exactly what the village looks like. In the middle, it is what the machine understands that needs to be produced. So we can actually evaluate the results of the machine based on the benchmark of what is, the truth, I would say, of what is on the ground. And you see, it's actually very similar. So as part of the training and testing experiments, the model which was trained only on the morphology, was actually only trained, on the morphology of Jizr az-Zarqa, but we also used it and we tried to train it on other settlements. So this is actually the example that you see here on the planned orthogonal grid of New York. So we're putting Jizr az-Zarqa in the middle of New York, and we can actually compare how the machine is actually reacting to that confrontation with the grid of New York. And so what you see here is the demonstration on the way a machine learning model can be used as an urban design tool. The first image shows the current state. Let's try to see if I can show it again. Here we go. The first image shows the current state of Jizr az-Zarqa, followed by 6 iterations of the model that generates new urban fabric based on the surrounding context and the existing pathways. We do plan to send that to the Ministry of Construction and to ask them to review their plan for Jizr az-Zarqa on that research. I'm not sure they will accept it, but we can always try. And so I would like to finish today with a project that is an ongoing project in which I'm very happy that Giorgio, he just doesn't know about it, but he's going to be very involved with this project. He's already involved with this project, but you will be more involved than ever on this. Just in a few words, a current project produced by PhD candidate Ethan Mann. Ethan was actually here with us just a few minutes ago, but he had to actually travel back to Israel, so he couldn't be here with us now, but he will join actually tomorrow's session of your lab online, so he will be able to talk about that more. Generative heritage, augmenting sight and story. Tangible cultural heritage refers to the physical artifact produced, maintained, and transmitted between generations. Intangible cultural heritage indicates the practices, representations, expressions, knowledge, skills, as well as the instrument, object, artifact, and cultural spaces that are associated with it, that communities, groups, and in some cases, individuals recognize as part of their cultural heritage. That's what the UNESCO is saying. The tangible cultural heritage and the intangible cultural heritage. Tangible and intangible cultural heritage are seen as two separate entities of cultural heritage assets, due in part to the technical limitation of recording them in conjunction. In this research, PhD candidate Ethan Mann wishes to follow the UNESCO 2008 Declaration on the Preservation of the Spirit of Place, reframing tangible and intangible as inherently linked, and develop the framework to preserve heritage as such. How to reunite the narrative of a place with its physical condition. How do we do that? How do we bring the text and the image together? The storytelling and the physical space. What lacks, and what Ethan Mann aims to develop in this research, is a technological framework to record and disseminate these interrelations. So Jason, this is very much related to our discussion as well, and I know that this is also very much part of your own research. In fact, technologies allows us to probe the situated knowledge that resides in dynamic and contested memories. They have the potential to revolutionize the role of a place in the humanities by moving beyond the two-dimensional map to explore dynamic representations and interactive systems. Digital media triggered an explosion of interest in narrative, linking tangible sight and stories. Stories are accounts of what happened to particular people in particular circumstances with specific consequences, and that constitutes a fundamental strategy for coming to terms with time, process, and change. In contested sites, and we've got many of those in Israel, as here actually, there is a challenge, and the challenge is to preserve the two aspects, the site and the narratives. The game changer here is the technology. In the research at the Material Topology Research Lab that we're having at the Technion, Ethan Mann develops techniques to capture both and link them, recording and analyzing the physical site through remote sensing technologies, collecting and analyzing stories using natural language processing techniques. So let me just show you that example. Here you see the recording of an ancient village of Lifta that is located outside of Jerusalem, a village that was part of the Jewish history, then part of the Palestinian history, then again part of the Jewish history, and so on. A village that is today empty, that is left over, and there is actually a plan by the Ministry of Construction to erase it and to build a fantastic, enormous real estate development on that site. We are trying and we are fighting to preserve it, but meanwhile we are also documenting it. And that's what you see here in the work of Ethan, that is about 3D scanning that site. We see here all kinds of sacred places that belongs both to Arabs and Jews, and we are documenting that. We are documenting those layers of histories. We don't talk about history, we're talking about histories, about narratives that are all very different, considering the different viewpoints of the different communities. And in terms of collecting narratives, we are using natural language processing as a computational framework that is used to teach a computer to understand the contents of documents, including the contextual nuances of the language within them. The technology can then accurately extract information and insights contained in the document, as well as categorize and organize the documents themselves. It is, Jason, what you were mentioning about that importance of the keywords, and this is actually what we are trying to extract through those techniques of natural language processing. Through merging real and virtual worlds, and through the production of new environments and visualization, extended reality technologies hold the potential to generate thick representations of locations holding contested, sometimes conflicting narratives. And you see here how we are using immersive technologies in order to reunite the text, the image, the narrative, the keywords in complex organization. This means keeping the place its archaeology, the memories that are embedded into it as a raw material, to connect these raw materials to different networks, to allow the narratives of other times and people to be there. Use the affordances of this immersive and interactive space of design. And here is actually the main protocol that Ethan Mann is currently developing as part of his PhD studies, a method to generate a multidimensional database in constant evolution, a generative heritage tool. In other words, a tool that will be capable of continuously collecting archives and data, structuring it, and then processing it through multiple platforms. And so I would like to conclude here and question these three shifts that I have described as fundamental conditions in architecture today. As we've seen, the movement from non-image to image, from an idealistic to a statistical form of architecture, and its transdisciplinary condition of knowledge have triggered, in fact, in architecture an approach that in a way transform our environment or reveal the environment as more than ever unstable and full of potentialities. And so I would like to conclude here by saying that all those projects you've seen are actually, I think, proofs of those potentialities and the transformation of our environment being natural or cultural or social or even political. And so those projects, in my opinion, refers to a say by the Nobel Prize Ilya Prigozhin, who many years ago talked about a reality that is not longer being, but that is actually in a state of becoming. Thank you. This is important to me. Thank you. And that's the team. That's the team. Thank you so much.
Thank you so much, Aaron. It was a very, very rich and stimulating presentation. We are sorry for the extended presentation for those of you who had other stuff to do and you had to leave and obligations. Are there any questions from the audience? I mean, I have plenty of comments and things and remarks that we could discuss, but probably it's the time of the audience. For the audience, yes, please. Yes, yes.
Thank you.
Not more of a comment, since we're only two architects right now. Yes, only two. It's important to highlight the importance of architectural research with that aspect, because as architects we're not engineers in the traditional way. We're basically architectural research is more or less more towards concept making, new aspects to explore potentialities. So it's important to highlight where does the other professions come in. For example, in the first part you showed all the material research. Afterwards, after the research is done and the concept is done and the proof of concept is presented to the industry, here is my prototype. What happens afterwards? Where does the other professions come in? Where does the computer scientist come inside? Where does the material science come inside?
This is, thank you, Justin, for the comment, for the observation, that I also take as a question, and I'd be very happy to respond to that because I think it's actually essential. Actually, it's referring to that third shift that I've been referring to, that is the way architecture has been transformed or has been influenced or has embraced what I would consider as a transdisciplinary knowledge. Now, I am not talking about interdisciplinary knowledge. I'm not talking about multidisciplinary knowledge. I'm referring to transdisciplinarity. And what do I mean by this? I mean that whenever I sit at a table with experts, I want to be recognized as an architect that is coming with its own expertise. So now we have to define what is the expertise of an architect or of a designer. But it means that we are not, in our lab, we are not working as pseudo-engineers, or we are not pseudo-material scientists. We are working with material scientists, with engineers from the Faculty of Civil Engineering at the Technion and elsewhere as well. We are working with the Textile Institute of Israel when it comes to textile. We are searching always for the experts that can actually team up with us in order to develop our projects. Now, for the question about, architecture and us as architects, right? What is our role in this? One of the fascinating aspect of the history of architecture is that as architects we've been always inventing tools. And there is a whole history about architects inventing tools, and those tools were always invented in order to respond to a certain perception of the world, to a certain perception of the environment and of space. And so those tools were, if they were invented, is because there were no tools capable of expressing that perception. In all the projects I've been showing today, including the last ones that have to do with simulation and visualization, I think that we are actually inventing tools. We're inventing interfaces, and that's where I think that we have a role as architects, because we're having a certain perception of the environment, of the 3D modeling. We're having that, that expertise. And even if I would say engineers have a lot of knowledge in terms of design, their knowledge is still different than the knowledge of architectural design that we do have. And so I think that that's a reason why we need to team up. There is also a very fundamental history of relations between architects and engineers. And that history exists. Actually, Antoine Picon is one of the most famous historian to describe that. And I do really believe about that kind of interaction. So I hope that respond to that idea of what I mean by transdisciplinarity.
Thank you very much. More questions? Yeah. Who wants to go first? Okay. Nicolette first, and then.
Nicolette. Yeah.
Thank you so much for this presentation. It's absolutely fantastic. You introduced this collection of projects with the idea of cultural sustainability and how it's like inextricably linked to environmental sustainability. And I wonder if you could kind of speak a little bit more about the cultural sustainability of some of the projects that you've mentioned. They seem to capture some important aspects of heritage, but with some of them I miss the human element, and I don't see how some of these projects continue, in the technical space, or the technological or the digital space, but what happens to the humans, and what can we get out of projects like these? How are they sustainable for us and for culture?
Oh, sure. Oh, thank you very much, Nicolette. I think it's actually fundamental also to think what is the position of the human in relation to those technologies and to those tools. By the way, that is actually very much related to the work, to the very first project of Tom Shackett, where, Tom himself is talking about the distance, the distance that is more and more significant between, the operator and the machine. You see, if I'm having a hammer and a chisel, I have a direct relation to the stone. But as soon as I put it in the hands of a robot, there is this distance that is that is generated, and then the question is also, where's the human within this kind of system? That's definitely essential to think about that. What is, I think, very interesting also is that in most of the projects that are involving robotics today, and I'm talking about projects that we see from other institutions as well, we see how the human is actually still an incredibly important factor within the protocol of manufacturing, because the robot is capable of doing certain tasks, but there is always a level of complexity that the robot is reaching where those tasks needs to be actually brought back to the human. So there is this idea of collaboration that certainly needs to be investigated more, and that we absolutely need to start thinking about. By the way, interestingly enough, I know that this is a detail, but it's a significant detail. In all the images that you've seen, the robots are not in cages. Until recently, robots were always in cages. We had to cage robots because they were seen as dangerous objects, right? And the human should never be in the vicinity of a robot at work. We don't have those cages because there is nothing to do. We have to actually learn to work with those instruments and to collaborate. So there is a whole open question here. That's one thing. Now about cultural sustainability, which I think is a significant aspect of what we are trying to do in the lab. Each one of the projects that we've seen is actually referring to a certain historical or cultural condition that is also local. So my question on your question, I'm adding another question, and that's the question I asked myself. So we have all those tools. We're having orange robots. And those orange robots, we see them in many other institutions in the world, from Switzerland to Japan, okay? And my question is, how is my robot different than other robots, and how my robot is performing differently than other robots? I don't want my robot to be Swiss, or to be German, or to be Japanese or American. I want my robot to be Israeli. So how do I do that? You know? And I think that this idea of thinking about the digital, as a local culture today, I think is an interesting idea. Okay, I'm all for the globalization, but the local is equally important in my opinion. And so those robots, we are trying to bring them to learn things that are actually related to our culture. Crochet, by the way, just a couple of weeks ago, they have found, there were some archaeological excavation around the Dead Sea again, and they have found an object that is made out of a crochet that makes it the oldest crochet in the world. So there is a possibility that the crochet was born somewhere in that region. So that reinforces my opinion about crochet. But also more obvious is, of course, the stone industry. Now, the stone, I agree, the stone is definitely not an ecological material today. And we know about that, okay? We will need to replace stone with other materials. But what about that culture? Are we supposed then to put an end to that culture, or are we supposed to search for ways to continue or pursue or transfer that knowledge to the future generations as just simply a cultural fact? So you see, I think that the human is always present, but indeed at different stages of those experiments. At least I can say that it's very important to us.
Yeah, my question is more about, I'm very impressed about the flow of knowledge you have in your lab. And it's made by your people, by external collaborators, with ideas coming from all around the world. So I'm very curious about the way you are managing knowledge. The way you generate, the way you store knowledge, the way you are transferring knowledge, because after a number of years of this, and there is a lot of empirical knowledge there, so it's coming from things that are done, and coding this knowledge is not exactly writing a paper. It's another kind of process, so I'm very, very curious about it.
Well, I'm curious about that aspect as well. I have to share with you, and I'm very open to advices. I have to tell you, I'm very open to advices. No, but it's it's a crucial aspect, and I'm working on that question these days. The reason is because we are basically closing 5 years of research since we opened that lab. 5 years means that we have our first PhDs who graduated and have left the lab. They're all in postdocs around the world doing beautiful things. And so what happened with that knowledge? What do we do with it? So there are a few things. First of all, I think that for us, publications, and I'm talking about academic, but also popular publications, were an important tool in those 5 years in order to be able to record and transfer that knowledge, transfer it to others in the lab, but also beyond that. So publications are definitely important. The second thing is that, and there was a moment in the presentation where you could feel that, when a PhD, when Dr. Karen Libar-Sinai finished her PhD and moved on with a postdoc, we had another researcher joining us, and he's now taking that endpoint where Karen Lee reached, and he's now looking into it from multiple aspects, learning from Karen Lee's knowledge, and today deploying it in multiple ways, to such a point where hopefully we will be able to continue this collaboration beyond the walls of the lab. So that's what we are doing. But you're absolutely right. It's a challenge, is how do we transfer the knowledge from teams to teams, from researchers to researchers. And to do that, we are very much relying today on our know-how that is being recorded collected in the lab, as well as those publications that we are producing.
So you have somehow a model that is a Bottega model.
Yes,
So
absolutely.
kind of training on
Yeah.
and doing things together, so you will have the people they are working at the Bottega and
Exactly. So you see here some, researchers are incredibly important in that kind of process, but also research assistant. So we're having a series of research. There are two here in the Ronnie Hillel and Dorna Cash. We are expanding that part of the team with research assistant. They're actually being trained to all the technologies that others are being developed, so that whenever we're having new researchers coming in, we have that knowledge that is actually being transferred. Yeah.
Yes, thank you for the very interesting talk. All the aspects were very interesting. I was a little bit curious, and I actually liked most of them. The application that you learned how, let's say, an older city was built. You're trying to replicate that with machine learning. I was wondering, and I hope that maybe this one sparks an idea of me. I was wondering if you can implement modern city design rules. And the idea behind that, of course, is that older generations had different needs, let's say. So, for example, that paradigm, that village that you saw before, I think that was older than before modern cars and modern roads. However, let's say modern city have different needs. So I was thinking if it would be somehow combined, let's say, so to actually maintain the roots of this older village, but also to introduce, let's say, the solutions that modern city planning has to offer.
So this is exactly the objectives of Anna Boehm after this research moving to her PhD studies. That's what she's actually interested to do. But it's about, training the machine to multiple needs that are not only local needs, but that can also be needs that are coming from a higher hierarchy in the process, that can also be economical needs and requirements. Definitely there is a higher level of complexity. To add to that, that means also changing the protocol and programming the machines differently. For instance, creating multiple channels of learning and training, and then after that recombining them. So that's indeed the plan. I think that's actually a very interesting proposal to go in that direction, because the goal here was never to actually simply reproduce the existing, but actually to look into ways to emulate it. And so I think that indeed we need to actually think about this hybridization of the different models that exist. I think that the machine learning process could help us doing that, because it could help us actually keeping the complexity of what it is to create an environment without such a key master plan. I can see there multiple applications indeed. Salvatore.
Actually, comment that was exactly on work on Anna Web. But first I would like to share a comment. First of all, thank you for showing how to stretch the design space and possibilities in architecture, but actually in the way in which we conceive space and our interaction with space. So from a simple tool to reconstructing film. This is quite interesting, how these pieces can be combined to generate something that is intangible. This is extremely interesting. And also how techniques or materials or approach methodologies that are typical in some fields can constitute completely new opportunities in other domains. So, and this is a sort of, I would say, way of thinking that we should maintain. Be flexible, open to look opportunities outside what is our domain. I was really, then the comment is quite provocative. Is about the generative work using machine learning, and with the objective of recreating a pattern that could in some ways, or at least developing an approach that could be able to replicate a pattern. So that not to let's say, getting that kind of contracts with the project developed by the urban plan office. I was interested in this since basically many years ago, some years ago. I was in contact with Spacemaker at the beginning. It was a startup. And they used the beginning genetic algorithm to automatize urban planning. And so the first time I saw this tool, they were doing all these beautiful things, different 10 options you could customize, and then you get this shape. I was in Toronto at that time, where the building, for some reasons, are a little bit simpler. And also this stratification is a little bit lower, since the technical materials are a bit less different than other places. And for example, they wanted at the beginning to implement some kind of evidence-based scientific reasoning. So for example, how we can use indication from video regulations in order to make it better, and having a design process that is more comprehensive, not limited to the prescriptive value of the light autonomy 2%, for example. And they implemented something, so it was an optimization problem, and we had this kind of thing. Then I provoked again them and said, okay, but if you switch the method from the light autonomy to the UDI, in fact it's called for lyrics, what's happening? Okay, the question was simple, was implemented, and suddenly, with the same kind of boundary condition, the dimension between buildings, the density, the distance from streets, or the if building could be attached or not, the shape of the neighborhood was completely different. Also, the 3D evolution, how did it was completely different. And then I said, okay, the method was why? But the metrics are different. Yes, of course, metrics are different. And the answer was, okay, we will choose which is the best. And the answer is the metrics are, by definition, simplification. It does not exist one metric that is the best. So in any case, it's a suboptimal thing. And I think that the beauty of architecture is exactly, of architectural brain, is exactly there, solving an optimization problem that takes into account some objective factors that depends also on needs and function and new requirements that in each period of our evolution we have, with something that is intangible, that is identity, that is also the desire to recognize pluralism. Also that was different from before, and was a desire, and architecture showed that kind of breadth. So the challenge is, I totally agree with you, and we're trying also to use. So machine learning, general technology is extremely valuable, is an extremely valuable tool. But it's a valuable tool in the hands of the person that understands that it is a tool, but sometimes I'm scared that having fully automated or pseudo-fully automated system, this will destroy that architectural brain that is able to really conceive new spaces just using a stone wall protecting or creating the conditions for that or its going to grow. So this is the kind of mechanism that sometimes I get a little bit scared. So it's very...
It turns out that I fully agree with you. So you know, I fully agree with you. I mean, one of the but here's the catch. I think that the problem, especially in architecture today, that we see with the use of computation, is in fact a sort of a positivist effect that is happening on architecture, where we create something, right, and we justify it quantitatively using computation, and we say, well, that's actually the most optimized version of what needs to be produced, meaning that's the good one. But then you look at it and you think like, well, it's not that great architecturally speaking. I mean, it doesn't matter. You know, it's like, so what do we do in this case? And so this is the, I think that where I join you is the fact that I'm not saying that, first of all, most of the things that I've been showing today, I'm not saying that as a cliche or as an easy way out, but I don't think that we are very much working on solutions. I think most of those projects are actually creating questions and problems that are, in my opinion, interesting problems. one of the problems about what we've seen with the machine learning project is where would you situate machine learning and that protocol within a much larger design task? Like, when does it happen, right? I mean, I can definitely see it at the beginning of a process as a way to create some kind of a milestone from which, you know, all those other very pragmatic, quantifiable operations needs to take place, what you refer to as optimization. But it gives you at least a certain or an interesting direction when it comes to, you know, what would be the continuity of a historical pattern, you know, on a certain terrain. And so at that level, I think that it is interesting, but it is definitely not an end of itself. Definitely not. What I'm not showing here, by the way, I just realized that as you were talking, I didn't show this, is that Anna has been presenting her research a couple of days ago, submitted her work, and there is a whole part that I haven't shown here that is actually all the statistics that she's actually extracting from those models, because she can talk about the height of the building, she can talk about the density of those models, she can actually make the comparison. It turns out that what I've been showing here, just roughly speaking, is that the machine is producing something that is very similar to the existing pattern, meaning that the machine is capable of being trained and to learn from that. But there are major differences, of course, between that kind of pattern and what, for instance, a government body would envision for that terrain for multiple reasons that are good reasons or not. You know, those differences also exist. Definitely something to investigate further and to think, you know, what should be the role of those operations in a design process at large.
Very strong opinion feeling about it, but I was saving that to discuss it with Aaron later instead of here, so that will give opportunity to others to talk from the audience. But just a very short note, I think that we have to, this is a totally wrong operation or practice that we keep doing of the town planning. We should ban town planning, I don't know. We should have like a very, very slow additive process of different scales, of working in different scales with different people, different stakeholders, and in that huge process there is definitely space for using automation to understand at least the design space of possibilities, okay, of potentialities, and configuration, just to be taken into consideration as a better insight of the different, you know, combinations of parameters and as different results. But just to say, okay, well, let's build a city, and I will stop here. Because I see that Fabio wants to say something.
Fabio, please.
Please. What you are suggesting is to take ideology out from the human processes, but I think that they will, before we do that, they will put ideology in machine learning, because if you start putting the layers of, let's say, directed approach in the machines, so you say, okay, we want more space for this, we want to open, we want to destroy because we want to increase the density. I was reviewing a paper from the Chinese group, and the approach was that one because of improvement of thermal performance. But the thermal performance was improving of 0.1 degrees, but the process was to clean up a piece of the town to make blocks. So, but in that case, they were performing better than in terms of and the approach could be done by machine learning. It's just tuning some properties.
Fabio, yeah, but you know, like I think, okay, first of all, I think that we're coming from a generation that at some point thought that it was the end of ideologies and that everything was possible and everything would be acceptable. And, you know, we're coming from that. the more the more I'm getting older, the more I do believe more and more in ideologies. I think that we need ideologies. Actually, ideologies is a way to be able to actually pursue the dialogue and the discussion, because architecture at the end is not a science. I still believe it is a discipline of opinions. And so I think that learning about those opinions is very important. So this is the reason why I do believe that actually in architecture, like in actually every discipline has been developing tools, and those tools have been always, I think, the reflection of certain beliefs and certain positions in the world, meaning certain ideologies. And I think that we have to accept that. Actually, that's the reason why I think that there should be a course on the history of tools, because I think that we will be able then to learn a lot of things about our multiple disciplines, being engineers, scientists, architects, designers, artists. And I think that it's actually very important. So ideologies, I think they exist. I think that we just need to make a decision as to who do we belong to. So we have to take position. And when we take position, I think that then we will know which tools to use for what. Anyway.
Are there any more questions? Probably we should be wrapping up. Yes.
Following what you said, Father, architecture is basically we are practicing and handling abstraction. So what the algorithm, how to structure the algorithm is to define design criteria, basically. In the design process, when designing a building, you want to have the abstraction of the client, what you want as an architect, what it's good for the client and for the city itself. This is a very abstract process. The design criteria is this type of definition, how you narrow down the parameters to something that is tangible, you can actually handle it. With machine learning or with data-level design, you actually expand your tool set and your control, because at the end of the day, you need some sort of control of the parameters. This is how you could define architecture.
My point is about complexity. Simple issue can be handled. So, for example, I made this study some years ago about optimization. So I started increasing the objective functions in a very simple way. It's building, optimization, thermal, visual, and other aspects. So moving from one objective function where the solution, you don't need neither a piece of paper and pencil, you know what is the right solution for that. Just increasing from one objective function to two objective functions, so a line and a space. Okay, you needed something to understand, but you can really understand why that is the best solution according to the solution. Then we move to 3. Okay, we start having the Pareto frontier, so different alternatives that are equally, if not equally good, but all of them are good, are not dominated solutions, okay, but you can understand why. Then I move to 4, and goes on this. With 4 objective functions, was really impossible. I start analyzing each of the 20 best solutions, and they had nothing to compare. And again, you can sort out that kind of complexity using, for example, a posteriori weights. So you weight them, and then at this case, do we need all this complex and hours simulation? If we set weights, we simplify the problem. So the issue is, this happens, the solution that I got was that this is what happens in the design brain. So the more knowledge he has, if you see Calatrava, he is very good in structure, so he uses a kind of...
but he doesn't know how to respect budgets. It's very expensive, so you know, he forgot that as one of the goals in the algorithm. Yes.
So, you see, this is basically, you can, from this example, you see how just setting you get the solution. And sometimes the beautiful thing of humans is that we make mistakes, each of us, but we are unique, and we do not replicate mistakes. The same mistakes are actually. I could say replicate quite a lot of mistakes. If we have solutions like SpaceMaker now in Autodesk, that easily provide, without efforts, the graphs, everything, I'm sometimes really scared then we will lose quite a lot of this complexity analysis that each designer until now has been doing. And also, it's important also to identify something, that what is beauty, what is identity of a space, is something that does not come from very simple prescriptive natures that we can code. It's something that is a little bit more complex. So I totally agree with Aaron saying there might be a room here to simplify, to actually not lose some opportunities into the design space, but it needs to be a process that requires to be controlled in some ways, and not fully outlined from the beginning to the end.
It relates to the other question, it's process of augmentation. So it's not about preserving a process of the fabrication process from traditional craftsmen. It's about augmenting the traditional craftsmanship into something more that hasn't been happening again. So you create something completely new. This is, you will basically stop doing portraits when we discover photography. Do we feel bad about it?
We can make up an example.
But those are probably the questions you say that your work is
when does the design stops and when does the optimization stops? You can optimize, but if you know that all the solution in front of you is good, you don't need an algorithm to tell you that it's good. Just do it.
What Salvatore is trying to make that actually we need to have a better understanding of where and why we use the algorithms and the optimization for the specific purpose. I think this is something that we all are
lead implication
But
about this kind of work.
Yeah.
Because how what you are doing is creating new ways to new boundaries between the human and the machine work.
Yes.
This is ideologically right from ideological positions. So would you recreate uncrafters in Israel because of the competition with Palestinians or with Chinese? Or you want to have another society where you have machines doing this work, competing with it's an ideological question.
Yeah, absolutely. Well, by the way, what for me is very interesting is that, that factory that you've seen of the Grabelski family is actually Israeli, but the workers that you've seen there are actually Palestinians. And if they are Palestinians, it's because they are the only one having that knowledge. It's a knowledge that is being transferred from parents to children in Arab families, and it's actually part of their own culture. So, I think that that's also a sign that, cultures are sometimes a bridge between communities and needs to be used for that. I think that in terms of the technology in this case, we are looking into how, the creation of those tools would be capable of sustaining those local cultures that are being shared by all those communities. So yes, I'm very happy if my orange robot would be today, fostering that kind of ideology of dialogue. I'm all for it. That would be actually a way for also reinforcing the idea that, of course, education, and in this case, research and education is, a binder between those communities. I find that very important, also as an opportunity. One little last thing about that discussion that developed here is that in many ways you actually refer to that second shift that I was referring to, the idea that the architecture is becoming statistical rather than idealistic. And this idea that the machine today is producing more and more models, that none of them, by the way, is ideal or the best one, but that they are all actually a flow of options. There are multiple ways of looking at that. One way is to say, well, what do I do with all this? Or the other way is to say, well, now technology is providing the architect with more options, meaning so freeing the architect from the idealistic model from which the architect can also make at some point a decision. And making a decision that is totally arbitrary, by the way, on that flow of options is, I think, also the role of architects and of researchers. So, you know, anything that we are producing anyway has, as Peter Gallison would put it, has a level of objectivity, but there is also a level of arbitrariness in what we're doing that makes that we say, well, you know, I'm going for that one actually. Greg Lean, who was one of the pioneers of digital architecture in his own time, was one of those who actually created the first models in architecture that were statistical, where he was producing more and more and more models. And one day somebody asked him, like, so now you have like 50 typologies of houses, which one do you want to build? And he said, well, I'll choose one of them, but if you ask me, I would have loved to build all of them. So you see what I mean? It's like, you know, there is a moment where for multiple reasons we have to make decisions, and they're, I think, also part of those protocols. Just have to make sure to make the right decision, I guess, in this.
Yeah, but probably we should be closing that's it. I just want to say one final comment that relates to it's like going back to the first comment, Nicolette's, okay? Since also it has to do with
Sure.
culture, and we are at least partly Stasi, okay, affiliated with Stasi, which is the issue of the technique, the craftsmanship and culture, and what do you solve with robots. I think it's like a very provocative discussion, because yeah, if we were to say that okay, this family or these workers, Palestinian workers, are the last in the whole region that they know how to do that, okay, how happy we should be about saying, okay, now we have managed to replicate them by having the robot, and we are, okay, let them die, we don't care, okay. Yes, okay, all right. But there is value in saving this part of knowledge, which is very relevant to what we are discussing here also in Stasi, in terms of the digitization. Okay, let's digitize all the monuments so that we have a digital twin of the monument. In case something goes wrong with the monument, we have all the documentation, okay, that we can refer back for its conservation. So there is definitely value in preserving knowledge and the craftsmanship. But the point that I wanted to make is that maybe I'm just saying, okay, trying to be provocative, that in the way that the construction industry is working, okay, by accepting some of the limitations of the reality and by saying that, okay, knowing that this is the construction industry, this is the parameters with which it is developing, okay, if we find cool new ways to facilitate and accelerate the introduction of of all this discussion of the ecological value of all these techniques and craftsmanship relating to life cycle assessment, footprint, carbon footprint, etc. Okay, to help the current clients of the construction industry, the people who will be living in these new constructions today, better understand and assign value to, you know, these qualities. Maybe there will be slowly again a new need, okay, that will be integrated in a different cultural thinking, okay, there will be transformation in our thinking, in our lifestyle, that we would want, there will be a need for such kind of workers, who will, again, then if there is need, if there is demand, they will, you know, start flourishing again as a practice. So this is how I read.
Yeah, absolutely.
Or I want to read. The regime is saving us.
As always.
The idea, you know, things are changing. It's great.
Yeah, I don't know if we should close.
I'm very much, no, I'm actually, first of all, I love the idea of keeping this discussion as an open discussion with open questions. I think that you're also referring in many ways to an aspect that I'm not talking about, that is the whole ethical aspect of those kinds of projects. I think that that's also an aspect that we would need to address at some point, because, you know, the fact of working with machines is not it's not an act that should go without, you know, bringing those sort of questions on the table, as, you know, for instance, you know, the social condition that it produced, the economy that it produced, but also the cultural value of that. I prefer to leave it open, but I do think that it needs to be addressed definitely within those kinds of projects and experiments. Great.
And this is the perfect moment for us to stop and close.
Thank you. Thank you very much.